All right, we are diving into one of the weirdest, most mind bending, and honestly, most important ideas in all of physics: quantum entanglement. This is the stuff that made even Albert Einstein scratch his head and basically forces us to rethink what reality even is. Okay, so let's get right into it. On one side, you've got your everyday experience, right? Your classical intuition. A coffee mug is a coffee mug. It's right there, it's separate from the table, and it's still there even when you're not looking at it. Simple. But then there's quantum reality. And when you zoom way, way down to the level of particles, the rule book gets tossed out the window. Down there, things can be linked in this really mysterious way, and their properties are kind of fuzzy and up in the air until you actually measure them. It's almost like they're waiting for you to look before they decide what they're going to be. So, to really get a handle on just how strange the quantum world is, let's start with a connection that makes perfect logical sense to all of us. Let's use the old glove analogy. Imagine you've got a pair of gloves. One's red, one's blue. You put each one into a separate sealed box, and you ship one of those boxes to a friend way out on the moon. The second you open your box here on Earth and see a red glove, boom, you instantly know with absolute certainty that your friend on the moon has the blue one. Now think about that. Your knowledge was instantaneous, right? But there's nothing spooky going on here. And why not? Because the outcome was set from the very beginning. One glove was always red, the other was always blue. All you did was reveal what was already true. This whole common sense idea, well, physicists have a name for it: local realism. Realism just means the gloves had a real, definite color all along. And local means that opening your box here on Earth couldn't possibly have changed the glove on the moon instantly. This was the foundation of classical physics, a universe that was sensible and predictable. But then, at the start of the 20th century, this new kid on the block called quantum mechanics showed up, and it threw a huge, deeply unsettling wrench into that whole classical picture. And here is where everything we think we know just breaks. Unlike those gloves, entangled quantum particles do not have predetermined properties. So a particle's spin, for example, it isn't up or down. It's in this weird, fuzzy state of being both at the same time. It's only at the exact moment you measure it that it snaps into focus and chooses one or the other. That quantum color literally isn't decided until somebody looks. You know who absolutely hated this idea? Albert Einstein. He just could not accept a universe that seemed to rely on chance and observation like this. He was convinced that quantum theory had to be incomplete. He thought there must be some hidden variables, just like the glove colors, that were telling the particles what to do all along. He famously dismissed the whole idea as spooky action at a distance. So here's the absolute heart of it. When two particles are entangled, they're not really two separate things anymore. They're described by a single, shared quantum state. That means if you measure one particle and find its spin is up, you instantly know its partner, whether it's across the room or across the entire galaxy, has a spin that is down. It's an instantaneous connection that just doesn't care about distance. So this set up a massive showdown in physics. Was Einstein's common sense, local realism, the right way to see the universe? Or was reality genuinely, well, spooky? For a long, long time, this was just a debate for philosophers. I mean, how could you possibly design an experiment to test for hidden information that, by definition, is hidden? The huge breakthrough came in the 1960s from a physicist named John Bell, who figured out a brilliant way to actually put it to the test. Okay, the absolute genius of the Bell test is in its logic. Here's how it works, simplified. You create a ton of these entangled pairs, and you shoot them off in opposite directions. Now, here's the kicker. At each detector, you randomly change what you're measuring at the very last possible nanosecond. The idea is, if the particles had hidden instructions from the start, like our gloves, there's a mathematical limit to how often their measurements can match up. It's a statistical ceiling. But if they are truly linked in this weird quantum way, they'll be correlated more strongly than any classical hidden instructions could ever allow for. They'll break right through that ceiling. And the verdict? Well, it's in. And it's not even close. For decades, one experiment after another, getting more and more precise, has shown the exact same thing. Bell's inequality is violated every single time. The correlations are stronger than our classical intuition allows. Quantum mechanics is right. And on this point, Einstein was wrong. Reality is fundamentally non-local. So, if our universe is officially spooky, what in the world are we supposed to do with that? What does a non-local reality even look like? Well, this is where things get even crazier, believe it or not.
There isn't one single answer that all physicists agree on. You got different interpretations. For example, Bohmian mechanics says, yeah, particles have real positions, but they're guided by this invisible, non-local wave function that connects everything instantly. It just fully embraces the spooky action. Then you have something totally different, like the many worlds interpretation. It says the wave function never collapses at all. Instead, every measurement just splits the entire universe into parallel timelines, one for every possible outcome. So in that picture, there's no spooky connection, just, well, an infinite number of views, each seeing a different result.
So what does this all boil down to for how we see the universe? That brings us to our final and maybe most profound takeaway. No matter which of those wild interpretations you lean towards, the basic lesson is just staggering. The universe is not a collection of separate little things bouncing around. It's a deeply, fundamentally interconnected whole. Those two entangled particles, they aren't really two things. They're part of one system, described by one single bit of math that just happens to be in two different places. What you do to one part here instantaneously influences the other part over there. And this really forces us to look at our most basic assumptions about how things work. This quote really gets to it. The correlations we see just don't fit any normal story of cause and effect, unless you allow for some kind of influence that doesn't have to obey the speed of light. Now, to be super clear, this doesn't mean we can send faster than light text messages. We can't. But it means the universe has this underlying connectivity that operates outside our normal rules of space and time. And that leaves us with one last, truly mind-bending question to chew on. If entanglement means that two particles, even light years apart, are somehow still one system, what if they aren't truly separated by the space between them? What if space itself, the very fabric of our reality, isn't the fundamental barrier we've always thought it was? Entanglement doesn't just challenge our view of the objects in the universe, it challenges the very stage they exist on, leaving us with a picture of reality that's more mysterious, more connected, and frankly, a lot cooler than we ever imagined.